So we're going to have to find the inverse of logarithmic functions also. And we already know to find the inverse of any function, we must switch x and y and then solve for y. And I'll give you an example right here of switching the x and the y and then solving for y. And we're going to do the same with logarithmic functions. You're going to switch x and y and solve for y, but you're going to have to apply a few tricks. The trick is you could magically add a log base anything to both sides of your equation, or you could raise both sides of your equation to be the powers of the base of your choice. So that's the trick that we're going to be learning today. So right here on this exponential growth function, we could find the logarithm, we could find the inverse, which will be a logarithm. We find the inverse by switching the x and the y, and then solving for y. But the problem is y is an exponent right there, and we don't want an exponent. We want that y to be a regular y. So what we do is magically add a log base 6 to both sides of this puppy. What was I thinking? Yeah, add log base 6 of both sides of this equation and watch the magic happen, right? So if you put log base 6 right there and log base 6 over here, the log base 6 of 6 cancels out. The y comes down. You don't have to do that because I actually do it for you right here. Check it out. It says log base 6 of x, log base 6 of 6. We know that that cancels out. The y comes down. There's your y. And here's your log base 6 of x right there. So as you could see, the inverse of an exponential growth function is a logarithmic function. And we also said that we could find the inverse of a log by the shortcut. Like, so if I give you this exact one, let me write it. Y equals log base 6 of x. The shortcut for finding the inverse of it when there is no h or k is to simply cover up your log. Cover up your log, and then it looks like the inverse of it, which would be an exponential growth function, y equals 6 to the x power. Make sense? No? Yes? Some of us, not all of us. Okay, so get rid of that guy. Let's move on to this next example. Example 2, find the inverse of y equals ln of x plus 3. So what is ln really? That's a natural log, but what kind of log is that really? Log base what? 10. Common log is log base 10, but natural log is log base e, right? E is an irrational, crazy decimal, right? So we're going to switch to find the inverse. We're going to switch x and y. So x is on this side, y is on that side, inside of the parentheses. And now you want to get rid of this log, which is really log base e. So how could we get rid of a log? By raising it to be the exponent of the base of whatever you want it to be. So because ln is log base e, I'm going to take the entire right side of this equation and raise it all to be the power of base e. And what I do to one side of the equation, I must do to the other side. So I'm going to take this x and raise it to be the power of base e. So what I really have is e to the x equals e to the ln of y plus 3. And e to the ln, e to the log base e will cancel out, and the 3 plus y will come down, and you will have e to the x on that side. Let's continue up here on the right side. And that's exactly what I'm showing. When I raise both of those sides of the equations to be the powers of base e, right here the e to the ln will cancel out and the y plus 3 comes down, and e to the x stays e to the x. So I still need to solve for y, so I need to get rid of this plus 3 by subtracting 3. And if you subtract 3 on both sides, you end up with your final inverse function of the natural log function. And your inverse function is y equals e to the x minus 3, which is the inverse of y equals ln of x plus 3. So let's practice and let's find some of these inverse functions. Let's all do number 1. First of all, how would we find this inverse? Switch x and y, then solve for y. Okay. What's the inverse going to be without doing any math? Y equals 7 to the x power, right? The shortcut, the trick I showed you is if you just cover up the log, you could kind of see your inverse right there. It says y equals 7 to the x power. So let me just prove it to you. Let's actually switch x and y. X equals log base 7 of y. And now let's solve for y. But the problem is y is inside the logarithm of base 7. Right? So we don't want this log base 7. We want to eliminate the log base 7. So how do you eliminate a log? By raising it to become the power of the same base as your log. So if you take this entire right side and raise it to be the power of base 7, and of course what you do to one side, you do to the other side, raise the x to become the power of base 7, and your new equation's right here, 7 to the x equals 7 to the log base 7 of y, then we know that the 7 with the log base 7 eliminate, and the y will come down, so you have y equals 7 to the x. There's your inverse of the original log base 7 of x. Do you have to do all that work? No. Why not? Because we know that awesome trick of covering up the logarithm, and you could actually see your inverse right there. And this only works when there's no h or k. If there's an h or k, you can't do this, right? So y equals 7 to the power of x is the inverse of y equals log base 7 of x. Number 2, what would I do to find the inverse there? Switch y and x. Okay, so let's start by putting x equals 8 to the y. Now, I need to solve for y, but y is an exponent. I don't want an exponent. I don't want it to be an exponent. I want it to be a regular y. How am I going to bring down that exponent y to become a regular y? What kind of log? Log base 8, right? Log base 8. If you put a log base 8 of the 8, that'll cancel out the 8, and the y comes down from the exponent to be a regular y. And what you do to one side, you do to the other side, apply a log base 8 over here on this side. You have to do what you do to one side, do to the other. So again, what happens here is log base 8 of 8, that cancels out, the y comes down, and log base 8 of x is your answer. Log base 8 of x is your answer. Probably write it the other way around. Y equals log base 8 of x. Number 3. What would we, or what should we apply right here? Or let's first switch x and y, right? X equals, finding the inverse of this, x equals e to the y plus 3. By the way, on this original one, just for funsies, is that an exponential growth or decay function? It all depends on your base. If it's greater than 1, it's a growth. If it's less than 1, it's a decay, right? What is the value of e? Decimal. What kind of decimal? It's 2.72 something. So it's definitely greater than 1, so this is a growth function. One more thing. Do I have an h value, an h shift, or a k shift on number 3? An h shift. Remember, h is always with x. And as you could see, x plus 3 is the exponent of base e. Anyway, we switched the x and the y. We switched them. And now we need to solve for y. But the problem is y is an exponent. And I don't want it to be an exponent. So I need to apply a logarithm to bring down that y. What kind of log am I going to apply? Log base e, which is really natural log. Okay, so if you wanted to, I mean, I guess you could write down log base e and log base e, or the better option, I mean, the more correct notation would be to write ln. ln of x, ln of e, and then you know that ln of e, it'll cancel out. If you do ln of e on your calculator, it'll equal 1 because it eliminates itself. There's nothing left. So what do we have here? We have ln of x equals y plus 3. So your final step will be to subtract 3. So we have ln of x minus 3 equals y. So y equals ln of x minus 3. let me ask you this. Is this a H shift or a K shift? It's a K shift, right? If it were an H, it would be inside parentheses with the X. So if I had parentheses around this thing, then yeah, it would be an H shift, but it doesn't have it. So it's just a K shift. Last one here, let's find the inverse. So let's switch X and Y. And now let's solve for Y. What should I do first? Get rid of that -3 by adding 3, right? It's this simple. Like on any equation, Y is on the right side of the equal sign. Let's get it by itself. What are you going to try to get rid of first? This base 2 or the -3? The -3, right? The -3 is by itself. It's really easy to get rid of a -3 by doing a +3. What you do to one side, do to the other side. So what do we have here? We have a x plus 3 on the left side equals 2 to the y on the right side. Now, in order to undo this exponent of y to make it a regular y, I need to apply what to both sides? A log base 2. So check this out. When I do log base 2, that will eliminate the 2 and the y comes down. But on the left side, if I just do this, log base 2, that's incorrect. Because I need to do it to both sides of the equation. And right now, it only looks like I'm doing it to the x, not to the 3. So in order to get this right, you have to do the whole side log base 2. Yes? If you don't put those parentheses, technically it's going to be wrong. The log base 2 of 2 cancels out. The y comes down. Y equals, you know what? I might as well write it on this side. Y equals log base 2 of x plus 3. Now, why are those parentheses so important? Because those parentheses imply an H shift, right? If you didn't have the parentheses, that 3 would technically be a K shift. So there is a big difference when we compare this guy over here, the y equals ln of x minus 3, compared to this one where there's log base 2 of x plus 3. Right here, there's no parentheses, which means that this is a K shift. Right here, there is parentheses, which means that this is a H shift. Well, technically, -3 is the H value. Do we get it? Okay, so I hope we understand how to find inverses and how to apply logarithms to undo exponents, or how to raise them to be powers to undo logarithms. See, the fact is, a logarithm, when you do the inverse, it's an exponent. And if you do an exponent, the inverse of an exponent is a logarithm function. So a logarithm undoes an exponent. Let's flip this paper over, and we'll see some more graphing. And right here I explain how confusing graphing logs could be by jumping straight into an XY table. Because if you're thinking of y equals log base 3 of x, and if you were to think of an xy table, you can't even plug in 0. You can't. Why not? Because you can't do, when you're thinking 3 to what power gives you 0, it doesn't exist. Does that make sense? So it gets really confusing when you start thinking of actual inputs going into this logarithm when you're thinking 3 to what power will give you this answer. It gets really confusing. So what I recommend is to graph the inverse of the log. So like this guy right here, let me rewrite it. Y equals log base 3 of x. To graph this, I would rather graph the inverse of it. And what's the inverse of it? Y equals 3 to the x. That's the inverse of it, right? So if I were to graph y equals 3 to the x, the exponential growth function, it's really easy to get coordinates for that. Just use consecutive integer inputs. Plug in the easiest number, 0. 0 as an exponent, anything to the 0 power is 1. So the output's 1. And you could continue with the growth factor of 3 to make it grow on the outputs. So 1 times 3 is 3, times 3 is 9, times 3 is 27. It's off the graph. Going backwards would be not multiplying by 3, but multiplying by the reciprocal of 3, which is 1/3. 9 times 1/3 is 3, times 1/3 is 1, times 1/3 is 1/3, times 1/3 is 1/9, times 1/3 is 1/27. And that's already ridiculously small. As a matter of fact, I really can't accurately draw the difference of 1/9 and 1/27. Now, these are the coordinates of my exponential decay function. Now, we haven't ever done this before. Maybe it's a good idea to actually graph it. Let's actually graph it this time. Because the actual coordinates of this guy will be the xy values but switched. So the actual coordinates will be 1/27, comma, -3, 1/9, comma, -2, 1/3, -1, 1, 0, 3, 1, and 9, 2. So let's graph both so we could actually see the visual difference between the inverse compared to the logarithmic function log base 3 of x. So when I graph this one, I'm going to graph it in red. Y equals 3 to the x. Let's graph it in red. 0, 1 is a coordinate. 1, 3 is a coordinate. 2, 9 is a coordinate. -1 and 1/3. So check this out. When I go -1 on the x, 1/3 of the way up, that's not even halfway. And then when you go -2, 1/9, -2, 1/9 is even closer to the x-axis. And then -3 and 1/27, that's practically, I can't really draw 1/27. That's like right on the line. And we know it infinitely gets closer, but it never actually touches. That's what we call an asymptote. This is the asymptote right here. The y equals 0 line. And usually on exponential growth functions, your k value is that asymptote. So this is a growth function. Let's graph the actual coordinates of the logarithmic function log base 3 of x. So let me do this in blue. So I'll do this guy in blue. -3 and 1/27 and -3. So 1/27, let's go with something easier. 9, 2. How's that? 9, 2. 9 on the x, 2 on the y. There it is. 3, 1. 1, 2, 3, 1. It's right there. Let's go for 1, 0. 1, 0 is right there. Let's go for 1/3 and -1. So right here, you're going to go 1/3 of the way and -1. It's not even halfway. It's 1/3 of the way. And then it gets closer and closer and closer. And in this case, your asymptote is your y-axis, which is your x equals 0 line. So here's your graph. So compare the exponential growth function to the exponential decay function. Notice that it's really a reflection over the y equals x line. Right? That red graph is a perfect reflection, or the blue graph is a perfect reflection of the red graph. Does that make sense? And what does that really mean? That the x and the y values got switched, and that makes total sense because the logarithmic function is the inverse of an exponential growth function. So you don't have to graph both, you just need to be able to understand that to graph a logarithmic function, I would cover up the log, treat it as if it were an exponential growth or decay, get your coordinates, switch your x and your y values to get your actual coordinates of your logarithmic function. So this is a final graph, and it's important to be able to understand how to state the domain and range. What's the domain of your logarithmic function right there? X is what? Is it all real numbers? And we're talking about the blue one here. Does it go to the left forever and to the right forever? Victoria, what do you say? Does it go to the left and to the right forever on that blue one? Yes. This blue line exists over here in the negatives? No, it approaches this asymptote. What is that asymptote? It's x equals 0, right? Which means that this whole blue line, it never actually touches the x equals 0 line. It infinitely approaches it but never touches, which means that this whole blue graph is on the right side of 0. So how do you describe that? X is greater than 0. How about the range? The range of your y values, this really does go down forever to negative infinity on the y's, and it goes up forever. Even though it goes this way, it keeps going up, up, up to the right. So right there is where you have y equals all real numbers. All right, so I hope we could graph these next two for homework. This guy right here, all you got to do is identify your h and your k. What's h? What's k? Okay, so we're going to ignore h and k, and we're going to pretend that we're trying to graph log base 2 of x. How do we graph log base 2 of x? Pretend it's a exponential growth function, y equals 2 to the x power. So if you write that down right here, y equals 2 to the x power, make your input-output table using consecutive integer inputs, plug them in, get out your outputs, but to get your actual xy values to your actual logarithmic function, you're going to end up switching all these x and y values, okay? So I'll stop this video here. You guys could work on the rest. And if you haven't finished yesterday's homework, please finish it.